To finish off chapter 7, which is all that the midterm's going to be up to now, is we have two real topics to do. One, the major one, is tree diagrams, and it's been brought to my attention that we might need to practice a little bit more on these questions that say at least one, and question 10 and 12 are those. First thing we're going to do is tree diagrams. Remember, I built one and kind of sort of got to the end of it. And these guys are long and convoluted, and you're going to get one in the midterm because they're important. So an airline offers advance purchase fares to its customers. And basically, if you buy an airline ticket early enough, you get a discount, right? You get it for cheaper. If you've ever tried to go somewhere at very short notice by flying, aren't the flights to wherever it is extortionately expensive compared to what they would have been if you'd like booked it 2 months early? So that's essentially what they've got here. And so they gave us some information, and I'm just reading it through once, then we'll show you how you create the table. The airline noticed that 30% of its customers who buy a ticket don't take advantage of the advance purchase fare, and that the remaining 70% do. So the first branch are going to be people who, I'm just going to say, don't take the advanced purchase fare, and these do take the advance purchase fare. And they told us here that in this case, 30% don't do it. So 30% as a decimal is 0.3. And so the other 70 is 0.7. Now, in these questions, we're going to treat the probabilities as without replacement. In other words, the numbers don't change, right? Now, the next feature that we're going to add to this story is that some people just don't turn up for a flight. It seems unlikely, but they don't, right? They buy a ticket. A lot of business people, for instance, are really, and government workers, I'm sure as well, right? They're going to go to Kansas to go to a meeting, but the meeting gets cancelled, so they don't go, right? Something like that. So what is happening here is that some people are no-shows, and some people show up. And if you don't buy an advance fare purchase, you might not turn up, or you might turn up. If you do buy them, you also might be a no-show, or you might also show up. And they tell me here, let's read this. The no-show rate for those who buy advance purchase fare is 45%. So the no-show rate for those who buy an advance purchase ticket. So advance purchase ticket. The no-show rate is 45%. So how many of them do show up if 45% don't turn up? It's always the same, right? They always add up to 100, right? Or in this case, 1. So 45% don't show up. How many will show up?
65%.
Okay, putting it 55. Now, the other group, the ones who, the no-show rate for those who don't buy is, oh,
I think you got it backwards.
I got it backwards. I did, I got it backwards. For the second group, those who do have, it's only 10%. So the no-show rate for this group is only 10%. And so 0.9. Okay. It's a bit like reading a document. You have to read it about 4 or 5 times, but eventually you created this table, and that's what you're after. In the homework, that's called A, that's called B, that's called C, that's called D. This guy's called E, and that one, for some reason, has decided to call it H. So you've got a whole load of things here where you say A is 0.3 and B is 0.7. Now, at the end, we have the final probabilities. Now, you get a probability, right? And there's 4 different finishing events by multiplying together the pathway that took you there. So 0.3 times 0.45. 0.3 times 0.55. 0.7 times 0.1. And lastly, 0.7 times 0.9. Now, the way I'm constructing this is pretty much the way you're going to be doing all of them. So knowing how to do this one is basically going to show you how to do the others that go along with it. Now, if you multiply these together and find out what they're equal to, you get 0.3 times 0.45, and this ends up being 0.135. The next one is 0.3 times 0.85, and this should be 0.2.
I think that should have been 55.55.
Well, this top one?
No.
0.3, no,
When you
this
entered
one
it
here?
into the calculator, it should have been 0.3 times 0.55.
Oh God, I can't read my own writing. That's a 5, isn't it? 0.3 times 0.55. That says 55, but when I wrote it down, it got kind of scribbled and I saw it as something different. So thank you for catching that. Now this one I can do is 0.07, and this one I can do is 0.42. Now I would have caught that mistake because this is the check that you do. See these final probabilities, right? There's one for each of these final destinations. What should they add up to if you do it correctly? So if you add all the probabilities of everything that could happen together, what should it add up to? What's the probability? 1, yeah, everything. So if I wrote down that wrong number, I would add them up and say, how come I'm getting 1.2? And then I'd do a quick check and see which one I got wrong. Right, so there is your probability tree completed. You find each branch by reading the story. You then multiply the routes like you're traveling along a road together. And these give you what are called the final probabilities. And in this question, they have a second part where they say, fill in this table, which I'm about to kind of draw.
Mr. Robertson,
Yes.
that last value should be 0.63.
This one? Okay, why? Because I can't read. I'm being really slow today. I mean, it's in front of me, yet for some reason I can't write things down. Too busy, I think, thinking of the next line. So what we're going to get here is people who show up and people who are no-shows. And total. And then we're going to have people who buy an advance purchase fare and people who don't. And we're going to get yet another total. And these guys here are going to help me fill in these 4 boxes here. The totals you get after you found those 4 guys. So each one of these corresponds to one of these 4 numbers. But in this story, we add one extra little thing. We assume, hypothetically, that this data was for 100,000 people. So this one here, see that 0.135? Isn't this people who don't buy a ticket and don't show? So the don't buy a ticket and don't show is where my finger is. See that guy there? That's him, right? They don't buy a ticket and they don't even show up. And that's 0.135, 0.135 times 100,000 people. And the answer that I have is 135,000. Now, this one is they don't get a ticket, but they show up. They don't get a ticket, show up. So they end up paying that one. And that's 0.165. I'm going to go to bed soon, I think. That's a 13,000. I shouldn't need a calculator for that. This guy here is 16,500. What about the one that goes here? People who buy these tickets and show up, right? So if you buy these tickets and you show up, it's that number. So it's 3,000. And what about the last group? They buy this ticket, but they don't show up. And that ends up being, I think it's 7,000. So you add these together and you get 70,000. You add these together and you get 30,000. You add going down the way and you get 79,500. And you add going down the way and you get 20,500. And if you add them all together, it should come to, and thank goodness it did, 100,000. And we have now finished part B. So part A was create this table. Part B was to pretend that this was done with 100,000 people. What would these become as numbers? And they would become 100,000 times each of these decimals. And then you find where they belong in that little table, and then you add everybody up. Now, question C, I'm going to pause for a minute. There we go. Getting some background noise. So question C says, use the tree diagram to figure out certain probabilities, or table if you want. So the first one is find the percentage of no-shows. So if I look at these 4 situations, the ones that mean people who didn't show up would be this one here, which is 0.135, which is 13.5%. And where else are the no-shows? This is a no-show. Where are the other no-shows? Because there's another bunch of people who didn't turn up.
The 0.0.
Yeah, that one.
Hmm.
Which is what? Another 7%?
Mhm.
And so the answer is 20.5%. Couldn't I also find the percentage who did show up? Couldn't I even tell you what that 7% meant? That 7% would be the percentage of people who don't get a special ticket but still don't show up as well, right? So you can do various combinations of these. In this case, the percentage of no-shows. In question D, given a probability. Given that a person is a no-show, what is the probability that they were an advanced purchase fare, right? So they buy an advanced purchase fare given that they were a no-show. And this table is actually going to be more useful than these. So I look at my table and I say, okay, if you're a no-show, doesn't that mean that you're only those people there? And so I know the bottom number is 20,500. Now, of those 20,500 of them, how many of them bought a ticket? The advanced purchase ticket, and that is 7,000. Are you comfortable about how the no-shows go in the bottom, right? So you get it from the column with the no-shows. And then how many of those no-shows bought a ticket? It's the top one, 7,000. And if I do that, well, I was going to do it as a decimal, but actually they want the answer as a fraction. So here goes, 7,000 divided by 20,500. Do a math fraction button, and you get 1441, which is actually what they say it is, so it must be right. I think that would be more sensible as a decimal. Basically about 34%, if you wanted to know. So if somebody doesn't show up, the chances that they bought one of these advanced purchase tickets is 34%, which is ridiculous. They must have money to throw away. Well, take that back. Don't you, if you buy an expensive ticket, which I never buy, can't you get one of those tickets where if you don't show up, you can use it again later? You know, if you want to get the really cheapest tickets, which I tend to do because I'm Scottish, is that you get, if you don't turn up, hard luck. You know, you've paid the money, you're not getting it back, right? Or they have a hefty transfer fee, right? So if you want to change the times, you know, it costs you so much money that you just say, nah, just no bother. Right? Are we cool on that? Right, so long question, I understand that, but good question. It says, refer to the answers found in part D, which is this answer. Write a sentence representing the result that someone with no training in statistics would understand. Well, I think the choices that they've given you are here, but the one that is the one I would choose says, about 34% of customers who do not show for this route had purchased an advanced purchase ticket. Just kind of what I said a few minutes ago. So a lot in that. First, you have to construct the tree. Second, create a table. And then lastly, answer questions using either the tree or the table. I've got time for one more of these, and then we'll have to go on to them. So let's see what we've got. Has anybody got a preference? 8, 9, or 11? Has anybody started the homework and say, I'd like you to do 8, 9, or 11? You don't care? But I will do
8.
Sure. So in question 8, consider randomly drawing 2 students without replacement. So this is a without replacement. That's a big thing. So if the question doesn't mention without replacement, you will assume that it is with replacement, right? So nothing changes, right? But this is without replacement. And there are 50 students, right? And those 50 students, 3 are left-handed. And of course, that must make the other 47 right-handed. We won't have any ambidextrous people to make the question simpler. We are now going to create a tree diagram representing choosing 2 people from the class at random. So first person could be left-handed, right? Or right-handed. 50 people. What's the chances that I pick somebody who is left-handed?
3/50.
Okay. Won't that make 47/50ths the chance that I pick a right-handed person? So far, so good? Now, second person could be left-handed or could be right-handed. Could be left-handed, could be right-handed. But the probabilities of these guys are not going to be 350 and 4750, 350 and 4750. That's what it would be if it was with replacement. But when it's without replacement, things get used up. So in this pathway, a left-handed person has already been chosen. So there's only 49 people, and there's only how many left-handed people to pick from now?
2.
There's 2. And do you remember the trick? If that's 2, this is what's left, right? Now, the first person was right-handed now. That's a different pathway. The first person we picked was right-handed. So there's only 49 people to choose from, but would you agree all 3 left-handed people are still there to be picked? So that would be a 3 out of 49. And what's left? The other 46 out of 49 are the right-handed people. Are we good? Now, in this question, they want us to do fractions rather than decimals, which is fine. That's what this thing's for. This one would be 3/50ths times 249. This pathway would be 3/50ths times 47/49s. This one would be 47/50ths times 3/49s. And this last one would be 47/50ths times 46/49s. And I'm just going to go 40 times 49 and tell you that the bottom number is going to be 1960 each time. Let's try that again. 50 times 49, 2450. Okay. Don't try and cut corners. You're not good at it. Right. So let's just do it from scratch then. 3/50ths times 249s, because I'd have to simplify it anyway if I thought about it. So that's going to be a 3 out of 1250. 3 out of 1225. Now the next one is going to be 3/50ths times 47/49. And as a fraction, that's going to be 141 out of 2450. That one cancels down differently, that's why. Next one, 47/50ths times 3/49. And that one becomes, oh, well, that's at least something. Same as the above answer. And lastly, 47/50ths times 46/49. That gives me 1081 over 1225. And that is that tree completed. And in this question, that's all they asked you to do, right? So they didn't ask you to make a table. But let's just pretend they did ask us to make a table. So what would we have? We'd have first person. It could be left or right-handed. And then we'd have a second person. And they can be left or right-handed. And this time I'm just going to fill in these guys. So for instance, if both were left, it would be this fraction here, 3 out of 1225. If you wanted to do a left and a right, it would be 141 over that guy. If you want to do a right and a left, it would be 141 out of that guy. And lastly, if you wanted to do 2 right, it would be that guy over 1225. I'm definitely not going to do the totals because those aren't very nice. Suppose they told you what would these look like, right, as physical numbers, right? You'd have to be told, well, we did it 500 times or something, in which case you'd multiply each of these by 500 to get it. That really doesn't lend itself to doing that. So the last thing we're going, sorry?
What would we put in the answer boxes, like the A, B, all the way to W?
Oh, well, that's A, and that's B, that's C, that's D, that would be E, and that would be F. And then they call these last 4 guys, these ugly fractions, for some reason they have a weirder lettering, but this is called K, this was called M, this was called N, and this would be called W. For the time that we've got left, then I want to spend doing these last 2 guys. There is a story attached to each. So in question 10, the probability that you win a game at a casino is 0.3. So I know that the probability that you're going to lose is 0.7, right? Because one is a complement of the other. In fact, we're going to be doing complements a lot in this question. So in this story, each game is independent of the other. That just means none of the probabilities change. We've done a question like this before. Remember the one where we figured out what's the probability that you get at least 1 boy, or 4 girls, that kind of question. So this is very similar to that. In this particular case, someone plays this particular game 4 times. And here's the probability that we're going to calculate. And the key phrase here, right, is at least once. In this case, what's the probability that he wins at least once? Now, if you try to calculate that probability by hand, wouldn't you have to find out, well, how many different ways could he win just 1 out of the 4? And then how many different ways 2 games out of the 4? How many 3 games? You'd be there all day, right? So what you do instead is you do a clever little trick and you find the opposite probability. So you have to kind of use logic a little bit. Remember the one where it's at least 1 girl? Didn't that mean they were all boys, right? It rained at least once. Didn't that really, the opposite of that was it was dry all the time. So what is the opposite of event of winning at least once?
Losing at least once.
Not at least once, but more than that. Definitely losing.
Losing every time.
Yeah. So the probability of getting at least one boy is all of them are girls. Right? The opposite of it raining at least once is it was always dry. Right? It's a total, everything's the same. Now, in 4 cases then, won't that be a loss, a loss, a loss, and a loss? Right? Isn't that how you lose 4 times in a row? And since the probabilities are independent, I'm doing this a slow way, don't you just multiply each one together? And they don't change value. And in this case, that is 0.7 times another 0.7 times a third 0.7 times a fourth 0.7, which if you do enough of them, can't you just write that down? So you might be doing this line and jumping right to that line. Now, on this, I can do it on my calculator. If you go 0.7 to the power of 4, we get the answer 0.2401. Now that's the probability that you lose all 4. And at this point, some people stop there because they think they've answered the question. But remember what the original question was. I want to know the probability that you win at least once. What I found is the probability that you lose all 4, which is the complement of that. But there's a rule or a law that says 1 take away the complement is the guy you're looking for. So do you see, once you find the answer, you just need to subtract it from 1 and you're done. So I don't know how to get that easily. So I find its complement. And then if you take the answer to the complement away from 1, it's equal to the original problem. You see the sneaky way of doing that question? Turn it into something that's easy to do and use that answer to get the one that you want. So in this case, 0.7599. You like that question, Cheyenne, don't you? Good. Right. Last one. A wait person. Where's what? Right. Somebody works in a restaurant, right? And the probability that they get a large tip is 20%. Will you always make sure that when you're doing 3 diagrams or these kinds of at least once, that you use the decimal version of the answer, right? Okay. So don't write 20 down, essentially. Now, this person is going to be waiting on 5 tables, and we're being asked to find what's the probability they get a large tip. Here's the keyword, at least once. It's another one of those guys. Now, a little extra. If the probability that she gets a large tip is 20% as a decimal 0.2, what's the probability that she's going to get a small tip then? Which that's what I'm calling the opposite.
0.8.
Okay. That's very similar to this one. What is the complement event? What's the opposite of getting at least 1 large tip?
Getting all small tips.
Right? Yeah. Which means small, 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 right? You did it 5 times. right? 5 tables, all of them are small tips. Not a very good night for her. Now, can I cut some corners and put in 0.8 to the power of 5? So I'm not going to write P of S times P of S times, and then 0.8 times 0.8, right? From here to there, a little bit quicker. And 0.8 to the power of 5 ends up being 0.32768. Right? So that's the probability of getting nothing but small tips. How do I get the answer to the original question? How will I find the probability of getting at least one large tip?
You would subtract the 0.32768 from 1.
And do your thing. Are we good with that? You might have to round off the answer. I don't know quite. Did they mention decimal? Oh, they want 4 decimal places. I guess I would round off a little bit. Check this is right. 6, 7, 2, 3. Yeah. Any questions about that particular situation? So 3 diagrams, you're going to get one in the midterm, so practice on them. Everything else is up for grabs. Your midterm is in 2 halves. This question, i.e. the tree diagram one, lends itself to being the one that you would do your working for, right? And you would be able to show me. And so that one's going to be one of the questions that's going to be in the Canvas, right? Now, the kinds of questions, because it's in 2 parts, remember, the 2 places. The first part is going to be on WebAssign and the second will be in Canvas. The ones that are being WebAssigned are really those questions that you would need to use SALT to get the answer. So you'll see a SALT in each of those questions. So you'd use it to do, I don't know, things like, the correlation coefficient, where you'd have to use SALT to get it. Or, I can't think of one off the top of my head, but I know there's others. Oh yeah, don't you need to, if you want to get standard deviation or a quick 5-figure summary or something, you might get it for those. And then section 2 will have, question like that, for instance, would work really well in Canvas. So would the tree diagram ones.
Okay, so on mine it says the probability of getting a large tip. Oh.
Are you good? Okay. Test is chronological order. So when you go in WebAssign, the first questions are like from week 1 and the last questions are from week 5. And when you go to Canvas, the same thing's true, right? The first question will be that. I haven't made the test, but I've got a kind of rudimentary idea of what it's going to look like. It's going to have 8 questions in both sections. So there are going to be 8 questions on WebAssign. There are going to be 8 questions in paper that you do. All working that you can possibly do, even questions that were on WebAssign, if you can think of some working to show me where you got your numbers from, that would help you get points as in partial credit.
Are we allowed to use our notes?
Yes. If it's physically written down, you can use it. You're allowed to use your TI-84 calculator. Obviously, you'll be using SALT in a few questions. So they're all up for grabs.
Sorry.
Well, you know, it's not quite the same, but I have puppies, so I have to watch because she likes chewing things. Actually, that's not that different. 2-year-olds probably chew things as well, right? But they shouldn't be chewing. And so you have to watch the little darlings because they
Yeah, I
get
just
all
caught
sorts
him
of
in the
things.
hamster bin pouring hamster stuff out.
Okay. Well, if the hamster bites him, he deserves it, right?
Amen.
Okay. Any questions? Because we're pretty much finished now. Is there anything you want me to go over before we say bye-bye?
Yes, could you help me get started on 11? Just like the first setup, not the rest of it.
Okay. Question 11 is, it's computers and laptops. Okay. So in the workplace, 30% of the people have computers or laptops. So lap for short. And that's 30%, which I'm putting in as 0.3, not as 30%. And the other lot have desktops. So I'll call them desk for short. And these guys are the other 70. And then 5% require servicing. So if you're looking at these guys, servicing, right, there's something wrong that needs to get fixed, and these have no servicing. And so they told us 5%. So that means the other 95% don't. And if you have a desktop, 10% needs servicing, while the other 90% don't need servicing. So you can imagine these are going to be the final probabilities. And then you want to build a table, and it'll probably look something like this. Lost the question here. Use a tree diagram to determine the percentage of computers and work that require servicing in a given month. So I don't actually need a table because they want to find the percentage that requires servicing. So the two that end up being situations where you end up servicing them is going to be that one and that one. So whatever that answer is, and whatever that answer is, if you add them together, that's the percentage that needs servicing. So there'll be decimals to start with, but if it's 0.23 when you're finished, the answer will be 23% or 0.23, depends. Oh, they want the answer as a decimal, so 0.23 would be what you would write. And if, or they want a percentage, it's 21%. Read it again because I'm not sure which. If it's percentages, write 21. If it's a decimal, write 0.21. Are we good? Right, have a nice weekend, but not too nice a weekend, because if you're having too nice a weekend, you're not studying. So get ready. If you spend the time and you're well prepared, there will be nothing in the midterm that should shock you, right? So you shouldn't be surprised. Hopefully you'll do well. You're not going to get a report from me. I just couldn't get it done, not with the getting, writing the finals and so on. It takes so much time. So what I will do instead is I'm taking Tuesday off, which is my personal day. I'm allowed one. And I will be using that to grade all your stuff and to make a report. So my goal is by late Tuesday, 7, 8, 9. Hopefully it's not 9, but it might be. I'll be sending you out an email and you'll be able to see what you got in your midterm and actually all your grade, right? Everything. And in case you missed a day, Sunday is a drop dead date. There are no extensions to homework or anything else. So if you ain't finished it by midnight Sunday, it's gone.